the sky over southern Iraq did not fade gradually on April 14, 2025. A wall of dust advanced across the landscape, swallowed roads and buildings, and turned daylight into a deep orange haze. In satellite images taken that morning and early afternoon, the plume expanded dramatically across southern Iraq and northern Saudi Arabia before powerful winds pushed it into Kuwait. Within hours, ordinary city life began to fail. Airports closed, schools in Kuwait shifted to remote classes, and drivers could barely see through the dust. Hospitals across Iraq received nearly 4,000 people with breathing problems, including roughly 1,000 cases in Basra and about 500 in Najaf. And that is the event behind this story. But the title needs one precise correction. The storm did not darken every city across the entire Middle East, and no official source measured the regional transition in a matter of minutes. And the strongest verified version is still dramatic. A massive dust storm swallowed cities across Iraq and Kuwait, and satellite observations showed the plume intensifying sharply within a little more than 4 hours. The sky changed quickly because the atmosphere had found a landscape ready to break apart, and strong winds were the immediate trigger. But wind alone does not explain why so much material entered the air, and the storm moved across one of the most important dust source regions in the Middle East: the dry Mesopotamian plain, the lower Tigris and Euphrates basin, and exposed soils extending toward northern Saudi Arabia and the Persian Gulf. Where water has declined, vegetation has thinned, and where vegetation has thinned, soil lies exposed. And when the right pressure pattern accelerates the wind, the ground becomes part of the atmosphere. That is the central thesis. The darkness was not created by a cloud arriving from nowhere. It was built from millions of particles torn from dry surfaces, lifted into turbulent air, and transported across borders faster than cities could adjust. The ordinary interpretation is that a dust storm is simply desert weather, and the dangerous exception is that human water use, drought, land degradation, and regional atmospheric circulation can combine to turn a familiar seasonal wind into a transboundary public health emergency. A dust storm can appear to be one event, and its causes have been accumulating for years. The April 2025 plume became visible from space, but its most important effects occurred near the ground, where people live and breathe, and coarse particles irritated eyes and airways, while finer particles penetrated deeper into the respiratory system. Visibility collapsed along roads and runways, outdoor work slowed, and emergency departments filled while the dust continued moving east. The event did not require a cyclone, tornado, or thunderstorm to produce a wall-like arrival. Dust storms form whenever strong, turbulent wind exceeds the threshold needed to lift loose particles. And thunderstorm outflow can create one type of advancing dust wall, often called a hadoob, but broad pressure gradients and seasonal winds can also mobilize dust across a much larger region. In Iraq, late spring and summer are the main dust season. Northwesterly winds known as the shamal frequently sweep down the Tigris-Euphrates corridor and across the Gulf. During the April 2025 event, powerful westerly and northwesterly flow crossed exposed land, gathering dust as it traveled. The storm did not carry one uniform material near the source. Larger sand grains moved close to the ground through short jumps and rolling motion. Smaller dust particles climbed much higher, remained suspended longer, and traveled hundreds of kilometers. And the smallest fraction could pass over one city and continue toward another country. This is why the phrase sandstorm can hide the real health threat. And the dramatic wall may contain sand and larger particles, but the air behind it can remain loaded with fine dust long after the leading edge passes. The darkest moment may last a short time, and the exposure can continue for hours or days. Satellite instruments capture the regional scale, but a satellite does not breathe the air. On the ground, the storm arrived as a sequence of failures. The horizon disappeared first, and landmarks became silhouettes as streetlights and headlights turned on during daylight. Aircraft could not safely operate, while people with asthma, chronic lung disease, heart disease, and other vulnerabilities began struggling. For clear documentaries that separate the visible spectacle from the mechanism underneath it, subscribe and stay with us. And the real question is not how dust can turn a sky orange. It is why the ground across this region is becoming easier for the wind to lift. The answer begins with geography. Iraq sits between major desert regions and contains broad alluvial plains built by the Tigris and Euphrates rivers. And for thousands of years, water and sediment created productive wetlands, marshes, farms, and river landscapes. But an alluvial plain can become an enormous dust source when it dries, and fine silt and clay are exactly the particles capable of remaining airborne for long distances. If the surface loses moisture and vegetation, those particles are no longer held in place. Repeated drought, reduced river flow, drained wetlands, overgrazing, disturbed agricultural land, and poorly managed soil can all increase the amount of material available to the wind. The storm begins in the atmosphere, and the supply is prepared on the ground. On April 14, 2025, the atmosphere supplied the force. NASA's Terra and Aqua satellites passed over the region at different times that day. Between about 9:30 in the morning and 1:50 in the afternoon local time, the later image showed dust activity expanding dramatically over southern Iraq and northern Saudi Arabia. And that 4-hour contrast is the best verified clock for the title. It does not prove that every street went dark at the same moment. Any regional plume can intensify gradually, while its leading edge strikes an individual city much faster. Video from Najaf showed an advancing wall swallowing the horizon, but the exact arrival time depended on location, wind, and distance from the dust source. And the satellite saw the whole system. A city experienced the front. As the plume crossed Basra, visibility fell and respiratory cases surged. Reuters reported that more than 1,000 people were taken to hospitals in the province, across multiple Iraqi provinces. Later reports placed the emergency room total near 4,000. Those figures must be handled carefully, and they were treatment counts reported during a completed event, not a measure of permanent illness and not evidence that every patient suffered the same level of harm. They still reveal how rapidly a dust event can overload medical services, and particulate matter is classified partly by size. PM10 includes particles with aerodynamic diameters of 10 micrometers or smaller. PM2.5 refers to particles 2.5 micrometers or smaller. The difference is not merely technical. Larger particles tend to deposit in the nose, throat, and upper airways. Finer particles can travel deeper into the lungs and may enter the bloodstream. Dust can also carry biological material, salts, metals, and pollutants collected from the surfaces it crossed. A plume that begins as mineral soil may become a complex air pollution mixture over farms, roads, cities, industrial zones, and dry lake beds. WHO describes sand and dust storms as a direct source of particulate matter pollution. Exposure is associated with respiratory and cardiovascular effects, although the exact health burden depends on particle size, composition, concentration, concentrates, exposure time, and the vulnerability of the population. And the orange color came from sunlight being scattered and absorbed by dense airborne particles. Blue light was reduced, leaving warmer colors to dominate. As particle concentration increased, even those colors dimmed. The sky did not become night. It became an atmosphere so crowded with mineral particles that daylight could no longer travel normally through it. Visibility is therefore more than a visual detail, viz., a measurement of how effectively light can pass through the air, and it becomes an operational threshold for aviation, roads, shipping, and emergency response. A pilot needs a reliable runway reference. A driver needs time to react. An ambulance needs to find a route without colliding with vehicles hidden in the dust. When visibility falls suddenly, speed becomes the enemy. The 2025 plume also demonstrated how quickly a national event becomes regional, and powerful winds carried dust east into Kuwait, where gusts reportedly exceeded 80 kilometers per hour. Schools moved classes online the next day to limit exposure, and residents were urged to avoid unnecessary outdoor activity. Northern Saudi Arabia was visible beneath the plume in the satellite imagery, but the event's strongest documented human impacts were concentrated in Iraq and Kuwait. That is why the final title names those countries rather than claiming that every Middle Eastern city was swallowed. And dust does not respect a border, but evidence still needs one. This transboundary movement creates a forecasting problem. The dust source may lie in one country, the strongest wind may develop in another, and the worst air quality may occur hundreds of kilometers downwind. They City can have clear skies while the dangerous air mass is already forming beyond the horizon. Forecast centers therefore combine weather models with dust emission and transport models. And the atmospheric model estimates wind, turbulence, pressure, moisture, and vertical mixing. The dust model estimates where exposed soil can emit particles and how those particles move, settle, or remain suspended. And satellite sensors show what actually happened, while ground stations measure the air people are breathing. Each system has limitations because clouds can hide dust in visible imagery, and bright desert surfaces can make detection difficult. Models may not know whether a field was recently plowed, whether a wetland dried, or whether a rain created a temporary crust on the soil. Ground monitors are sparse across many dust source regions. The storm can therefore be obvious to a camera and still difficult to quantify precisely. WMO's 2020-26 Airborne Dust Bulletin identified North Africa and the Middle East as regions heavily affected by major dust intrusions during 2025. The report emphasized that average global dust concentrations can remain similar from one year to the next, while specific regions experienced in bad preferencized and severe events. That is another important reframe. A stable global average does not mean a local hazard is stable. Dust is intensely uneven. One source region can remain quiet while another produces repeated plumes. One city can sit beneath clear air while another, only 200 kilometers away, loses the horizon. A yearly average can hide the few hours that close an airport and fill an emergency department. And for people in southern Iraq, the meaningful scale is not global dust mass. It is whether the next wind crosses exposed land before reaching the city, and the land beneath those winds has been changing. The 2022 dust season showed what happens when the same atmospheric and land system repeats the failure. From early April through the middle of May, Iraq experienced at least 8 major dust storms in roughly 6 weeks. Baghdad, Najaf, Sulaimania, and other cities repeatedly disappeared behind orange skies. Airports closed, schools shut nationwide. and government offices were suspended in several provinces while thousands of people sought medical treatment. One storm is a disruption, but a sequence becomes a national operating condition. The 2022 events also reveal why the April 2025 storm cannot be understood as an isolated freak occurrence. The storms were separated by calmer periods, but the source landscape remained exposed. Each new pressure pattern or shamal wind could lift another layer of material. The atmosphere reset. The land did not. That distinction changes how risk should be reduced. A city can prepare ambulances, airport procedures, school closures, masks, filtration, and public warnings. Those measures reduce exposure during an event. They do not remove the dust source. Source reduction begins with water and land. And the Mesopotamian plain contains dry river sediments, abandoned or stressed farmland, shrinking wetlands, saline soils, construction surfaces, and natural desert. Not every particle comes from human damage, and it would be false to claim that climate change or water policy creates every storm. Strong winds and arid landscapes existed long before modern cities. The supportive warning is narrower. Poor water and land management, drought, vegetation loss, and environmental degradation can increase the area of loose, erodible material. And doubly on those states that natural deserts remain major global sources, while human activities can worsen emissions by stripping vegetation and exposing soil. In Iraq, declining water resources are especially important because water once stabilized parts of the landscape. Moist soil requires more force to erode, while plant roots bind particles and vegetation slows wind near the ground. Wetlands add another layer of protection by trapping sediment. When those protections weaken together, the threshold wind speed needed to release dust can fall. The first particles then help release more. Wind pushes grains across the surface. Their impacts knock smaller particles loose, a process known as saltation bombardment. Turbulence carries the fine fraction upward. Once the plume thickens, its leading edge can become a visible wall. And this mechanism explains why the sky can change faster than the underlying environmental conditions. The land may dry over months or years. The atmosphere activates it in hours. Southern Iraq's marshes demonstrate the connection, and these wetlands depend on water flowing through the Tigris-Euphrates system. When inflow declines and evaporation intensifies, exposed sediment, salt, and degraded vegetation can become new sources of airborne material. And the same water shortage also affects agriculture and rural livelihoods. Farmers facing reduced irrigation may leave land bare. Shepherds lose grazing areas. Salt accumulates in soil. Families move away from places where crops and animals can no longer be supported. Dust is therefore not only an atmospheric hazard, it can be a symptom of a damaged waterland system. The International Water Management Institute described this pressure in southern Iraq in 2026, focusing on Daikar in the wider region. Its researchers argued that responding after a storm is not enough. Restoration, water management, vegetation, soil stabilization, and regional cooperation must reduce the conditions allowing dust to intensify. That approach is harder than issuing a warning. A forecast can be produced in hours. Land restoration requires years, and planting vegetation sounds simple, but trees and shrubs need water in a region already facing scarcity. The wrong species can consume scarce groundwater or fail in saline soil. A green belt that is not maintained can become another abandoned project. Restoration must match the landscape. In one location, native grasses may stabilize loose soil. In another, irrigation practices may need to preserve surface moisture without wasting water. Wetlands may need environmental flows. Agricultural fields may need windbreaks, residue cover, or reduced disturbance. No single wall of trees can stop dust transported from hundreds of kilometers away. Regional cooperation matters because the plume can cross several countries while the source lies far from the city experiencing the impact. And shared satellite data, weather observations, source mapping, and forecast products give governments more lead time. Lead time changes the consequence even when it cannot stop the wind. Airports can secure aircraft and adjust schedules, schools can shift activities, and hospitals can prepare respiratory services. Outdoor workers can reduce exposure before the worst conditions arrive. Road authorities can reduce its worst point. The warning has to arrive before the wall. And that is where modern forecasting still struggles. Dust emission depends on fine details at the surface, while atmospheric transport depends on rapidly evolving wind fields. A model may correctly predict strong winds, but underestimate how much loose material is available. It may identify the source, but miss the height of the plume. Artificial intelligence is now being tested alongside physics-based models to improve speed and pattern recognition. The 2026 WMO Bulletin highlighted the potential while also warning that no single approach performs best in every situation. A fast model is not automatically a reliable warning. It must be checked against satellites, ground monitors, weather stations, and previous events. And the April 2025 storm offers a clear test. A useful forecast had to predict not only strong wind, but the path from the dust source through southern Iraq and into Kuwait. It had to estimate when visibility and air quality would deteriorate in individual cities. The difference between a regional forecast and a street-level impact remained enormous. That gap is where people experienced the storm. The gap becomes most dangerous on roads. A dust wall can reduce visibility from kilometers to meters across a short distance. Drivers outside the plume may still see blue sky ahead, then enter a brown curtain before traffic has time to slow. Brake lights appear too late. Vehicles stop in travel lanes, and a collision can trigger another behind it. This is why the storm's visual drama and its operational danger are inseparable. The same wall that creates extraordinary images removes the information people need to move safely. Aviation faces a different version of the problem. Dust reduces visibility and can contaminate engines, sensors, runways, and mechanical systems. Even when an airport remains physically undamaged, safe operation may become impossible until the plume thins and surfaces are checked. And solar power also loses output when dust blocks sunlight or settles on panels. Electricity demand may rise because people remain indoors and use cooling or filtration. Water systems can be strained as dust contaminates exposed supplies, and communities need more clean water for washing. And the storm touches systems that were not designed to fail together. Transport slows as health demand rises, while power and water systems face additional pressure. At the same time, agricultural land loses another layer of soil. A single plume can therefore create consequences far beyond the hours of darkness. Dust deposited on crops can reduce photosynthesis, damage plant tissue, and bury seedlings. The source area loses fertile topsoil, while the receiving area gains material that may contain salt or pollutants. Repeated erosion leaves the land less productive and more vulnerable to the next wind. This creates another feedback in which land degradation produces dust, dust damages agriculture, and weakened degradation leaves more land exposed. And the feedback is not automatic everywhere, but it is one reason restoration and soil protection matter as much as emergency response. The April 2025 event also exposes a communication problem, and people often judge danger by what they can see. The wall looks most threatening as it arrives, so attention peaks during the darkest images. Fine particles can remain after the sky begins clearing. A city may look normal while air quality is still poor, and the end of the visual event is not necessarily the end of exposure. That is the documentary's midpoint reframe carried into the human consequence. The most dramatic moment is the advancing wall, the longer danger is the air mass, the deposited dust, and the land conditions waiting beneath the next wind. This does not mean every dusty day is an emergency. Dust concentration, particle size, duration, wind speed, visibility, and local health conditions vary enormously. And some events produce a light haze. Others reduce visibility to near zero. A regional plume can pass high above one city while contaminating surface air in another. The title describes a real severe event. It should not turn all Middle Eastern weather into one worsening catastrophe. The April 2025 storm was completed. It did not remain over Iraq and Kuwait indefinitely. Airports reopened, schools resumed normal operations, and the plume dispersed. And the current significance comes from what followed. In July 2026, WMO's latest airborne dust bulletin again identified the Middle East as heavily affected by major dust intrusions. And the report emphasized that dust harms health, transport, agriculture, water, energy, and ecosystems, while forecasting remains difficult because emission and atmospheric transport must both be modeled correctly. In April 2026, researchers working in southern Iraq described dust storms as part of a broader tipping pressure on rural communities already facing water scarcity, desertification, shifting dunes, and declining agricultural security. Those are not predictions of another storm on a specific date, and they show why the source problem remains active. Scientists and authorities will watch three layers. And the first is weather. Strong pressure gradients, shamel winds, cold fronts, thunderstorms, and turbulent mixing capable of lifting dust. The second is the surface, soil moisture, vegetation, wetlands, dry lake beds, agricultural disturbance, and the location of active dust. And the third is exposure. The city's roads, hospitals, airports, schools, farms, and power systems lying downwind. A dangerous event occurs when all three align. A strong wind over stable, moist soil may produce little dust. A degraded landscape beneath weak winds may remain quiet. A major plume passing over an unpopulated area may have limited immediate human impact. The crisis develops when a vulnerable surface, an efficient wind pattern, and dense exposure connect. That is why the location matters. In southern Iraq sits near major dust sources and along a pathway toward Kuwait and the Gulf. Basra is both a large city and a transport energy and port center. Najaf receives large numbers of visitors. In Kuwait's urban area, schools, roads, airport, and energy infrastructure can be reached by dust transported from beyond its border. The storm's footprint was regional because the systems it touched were connected, and the solution must be connected too. Forecasting can reduce immediate exposure, healthcare planning can reduce harm, and road or aviation procedures can prevent secondary disasters. Land restoration can reduce some emissions, while water cooperation can protect wetlands and agriculture. None of these measures eliminates natural dust storms, but together they can prevent every event from becoming the same level of crisis. The vertical structure of the plume also controls what a city experiences. Dust mixed through the lowest part of the atmosphere produces the worst breathing conditions and the sharpest visibility loss. Material transported higher above the ground may travel much farther before settling, creating haze beyond the zone where the original wall formed. Wind can also separate particles by size during transport, and heavier grains fall first, while fine dust continues downwind. This means the most distant city may never see the same towering brown front, yet it can still receive degraded air quality from the same regional event. The storm, therefore, has two footprints: the dramatic path visible near the source and the wider, less obvious path of suspended particles. The honest boundary is equally important. Climate change can increase heat, evaporation, drought pressure, and soil dryness. In regional water management, dams, irrigation, land use, vegetation, natural climate variability, and individual weather systems all contribute. The April 2025 storm cannot be attributed to one cause from the available evidence. Its physical sequence is supported. Dry and exposed surfaces supplied material. Strong winds lifted and transported it. The plume expanded across southern Iraq, northern Saudi Arabia, and Kuwait. Visibility and air quality deteriorated. Thousands sought treatment, and airports and schools adjusted operations. That is enough to make the event serious without inventing a simpler cause than the science supports. And the most useful question is not whether the Middle East will become permanently hidden behind dust. It is whether governments can see the next wall before people on the ground lose the horizon. Better satellites can detect the plume. Better source maps can show where the soil is vulnerable. Better models can estimate its path. Better alerts can protect people during the event. But the forecast only addresses the moving cloud. The deeper work begins after the air clears in the marsh, field, river, and dry soil left behind. Picture the final image. It is late morning in a city under a bright sky, and traffic moves normally. Shops are open, and airport runways visible from one end to the other. On the western horizon, the color changes. At first, it looks like a low brown cloud, but then the line rises and buildings disappear behind it, one by one. Sunlight turns orange, the road ahead loses contrast, and the airport tower can still see the runway for only a few more minutes. The wall reaches the city, and daylight collapses into dust. Hours later, the wind will move on, the particles will settle, and the skyline will return. But beyond the city, the exposed ground remains exactly where the storm found it. The sky clears, the source does not.